Greetings. This is the first installment of a bunch of little mini lectures that I'm going to make as part of sharing physics with you during this time of social distancing. And I'm going to do some demonstrations related to the material that we would have talked about in class, were we in class. So you'll be able to see me. Oh, and I can see you too as well. I need you to know that. I can look through your computer monitor. I put a virus on your computer that allows me to see you through your webcam. Don't think that I can't. I will be watching you. No, actually, but we will be staying very much in touch. The learning assistants, the teaching assistants, and I will be absolutely in contact. As we talked about at the start of this period, we are going to be doing instruction remote, but not isolated. We won't be isolated. We'll be in constant contact, and I'll have regular installments like this to show you some of the physics, to make some of it a bit more real. And today we're going to talk about the phenomena of electromagnetic waves and a concept called polarization that can be a little tricky to wrap your mind around. So I want to look at this device that I have right here, and this is a device that emits electromagnetic waves. And there's an antenna in the front, and I have these two wires right here. And there's a generator inside here that is putting a potential difference between this wire and that one. So it'll start out with this one positive and that one negative, and then it's going to switch so that this one is negative and that one is positive, and it's going to keep flipping back and forth. And when I have the oscillating potential difference, it's going to make an oscillating electric field. First, it's going to point down, and then it points up, and then it points down, and then it points up. And it's going to send out a wave of electric field, but also a wave of magnetic field. So it's going to have a wave of electric field. And the electric field will be pointing up, and then down, and then up, and then down. And we're going to say it's polarized vertically because the electric field is always on the vertical axis. There'll be a magnetic field that is always along the horizontal axis. And we're going to detect the electromagnetic waves, which are actually in the microwave region of the spectrum, with this device right here. Now this device has an antenna as well, and you can see there's two parts to it. It looks very much like the antenna on the emitter. The receiver has a two-part antenna. It's a dipole antenna. And if it's oriented along the vertical axis, it will pick up a signal because when the electric field comes in, if it's pointing down, it'll make the bottom electrode at a higher potential than the top electrode. If I have this antenna pointed sideways, the electric field is pointing vertically, I won't get the potential difference between these two sides of the antenna, and so I won't pick up a signal. So the polarization of the antenna has to be the same as the polarization of the wave for this to be able to pick it up. So I'm going to go ahead and turn my receiver this way. I'm going to turn my emitter this way. I'm going to turn on my emitter, and it takes a while to warm up. This was a device from back in the day when they had tubes inside. When I say it has to warm up, I mean it literally has to warm up. There's an electrode inside there that has to be heated so the electrons come off of it. And when they start doing that, I will be able to detect a signal at my receiver, and it'll make an audible signal. It's having microwaves that are transmitted, but they're modulated. The intensity, oh yeah, there's my signal right there. My intensity is modulated by that hum. It's a 60 hertz hum. That's it. That's my microwaves. But if I can stop the microwaves from reaching the receiver with a piece of metal, no more hum, no more hum. And so the metal will block the microwaves from reaching it. And it makes sense because this is a wave of electric fields that are going vertically, magnetic fields that are going horizontally. This metal is a conductor. And we know that electric fields can't go through a conductor. So the electric fields will stop here, and I won't get any microwaves able to reach the receiver, and so I can shut this down. But more interestingly, I can use this grating to stop the microwaves because this grating is a conductor along this axis because there are these metal bars. If I put it this way, there is no conduction along this axis. And so I'm going to be able to block the electric field of the electromagnetic waves if the bars are oriented this way. If they're oriented this way, there is no conduction along this axis. And so the electric field will be able to pass. And this is a grating that's known as a polarizer. If I had microwaves that were unpolarized, if I passed them through here, I would only get through waves with their electric field along this axis. It will block anything with its electric field along this axis. So we'll turn this back up again. And if I put this between the two, I'm able to stop the microwaves from reaching my receiver, because the polarization of the waves, which is vertical, matches the orientation of the bars. So the microwaves are just driving charges up and down in these bars, no transmission. But if I rotate it by 90 degrees, now the microwaves can make it through. Because the electric field is going vertically, there's no conductors oriented vertically, so it doesn't block those waves. Now another way I can stop the transmission is if I take my receiver and I rotate it by 90 degrees. Because now the electric field is going vertically, but the antenna only detects electric fields on that axis. Now I'm going to show you kind of a cool trick. If I take my polarizer and I put it there and I rotate it, it actually changes the polarization of the emitted waves so that I can pick up some of it here if I have it in the middle. And that's kind of an advanced topic. Think about that one. Give it some thought. Waves come in polarized on this axis. When they leave, now they're polarized along this axis. And so they will still reach the receiver. So this is how we do this, how we demonstrate polarization with microwaves. And I'm going to turn this off. And I'm going to turn off my little boom box, which was letting us hear the signal. And I'll show you another place where this shows up. So here's a radio, and this is a pretty cheesy garage sale radio from the Little Shop of Physics, but I'm going to crank this up, and it's set to pick up AM. Got some country and western. Awesome. Now, the antenna in here actually picks up the magnetic field component of the electromagnetic waves. And radio waves, AM radio waves, have their electric field vertical. The magnetic field is horizontal. So the magnetic field goes this way, and then it goes this way, and then it goes this way. There's a coil inside the radio oriented like this. And I'm having a change in flux inside that coil because the magnetic field goes this way, and then that way, and then this way. The change in flux produces an EMF inside the coil. That makes the signal that you hear. But if I take the radio and turn it this way, oh, heavens to Betsy, there's no more signal. That's because the magnetic field is going along this axis. I'm not getting any flux through the coil. And so I lose the signal. Now, if I take the radio and rotate it this way, same story. Now the magnetic field is going parallel to the coil. I don't get flux to the coil, no signal. My radio is only going to work when it's in one orientation. And that's because the coil inside here picks up the magnetic field. I have to have a component of the magnetic field through the coil. And that's one place in your daily life where this concept of polarization shows up. Now you can also have polarization of other kinds of electromagnetic waves. And I want to switch out the equipment, and then come back and look at polarization for visible light, because visible light is an electromagnetic wave as well. So we saw, when I had this device right here, we could use this as a polarizer. It won't let electric fields through if the electric field is directed on this axis, but it will let electric fields through if it's directed along this axis. So I only get electric fields which are polarized in this direction. They're polarized along the horizontal axis. Or if I turn it like this, I only get electric fields along the vertical axis. Now it turns out this piece of material right here, this is a polarizer for visible light. They're long chain molecules inside here that are oriented like this. They're oriented horizontally. Long chain molecules that conduct along their length. So if an electric field hits it going this way, it conducts, and electric fields can't pass through a conductor, so the wave won't pass. But if the electric field has, or if the electromagnetic wave has this electric field directed vertically, it can pass. So this is a polarizer for visible light. Now, right now, the light coming from my face is unpolarized, and so half of it will come through, so it looks dimmer. But if I take a second polarizer, right here, and I put this in front of my face, and I bring up this first one, if they're polarized the same way, you can see me. If they're polarized this way, you can't see me at all, because this one only lets light through that is polarized horizontally. This one lets through light if it's polarized vertically. So the two of them together pass nothing. I'll have horizontal polarization, vertical polarization, but now neither shall pass. And you've seen polarizers like this before in sunglasses. And sunglasses only let through light of a certain polarization state. And that prevents you from seeing reflections, because reflections from shiny surfaces are strongly polarized. And polarization is also used as an analysis tool in certain situations. And I'll show you an example. So this light that I have right here is polarized, has a polarizer wrapped around it. So it only lets through light that is vertically polarized. So if I put this filter in front, if the polarization of the filter matches the polarization of the light source, all the light comes through. But if I turn it this way, you no longer get the transmission. And so the light coming from here is quite dim unless I put something in between the filter and the light, which can change the polarization of the light source. So this fork makes a really cool pattern. And it turns out that the plastic in here, the molecules that make it up, change the polarization of the light, and they rotate the plane of the polarization. Starts out vertical, won't make it through unless it's horizontal, but it will rotate the plane of the polarization of the light, so some component of the light can pass through. And different colors rotate the polarization by different amounts, or different colors of light have their polarization rotated by different amounts. And here's also a plastic cup, and you can see it makes an especially interesting look on the bottom. And you can actually see the stresses that were left in the plastic from the molding process. And so this phenomenon of polarization absolutely works for visible light as well as does for radio waves and microwaves, because visible light is an electromagnetic wave. And the thing that determines the color of the light that you see is the wavelength or the frequency. Now we're going to talk about that whole concept of wavelength and frequency is related to the energy of what we call photons. But now I want to just take a second and think about that as a preview for the next thing we'll talk about. So the higher the frequency, the higher the energy of photons. So as you go from the red end of the spectrum up to the blue end of the spectrum, the energy gets higher and higher and higher, and the energy of ultraviolet is higher still. If I go to the other end, if I go from the blue down to the red, the energy of the photons gets lower and lower and lower. And if I go into the infrared region of the spectrum, the energy of the photons is so low, they don't interact with most organic molecules. For instance, the pigment molecules in my sassy teaching shirt that I'm wearing. And so to close, we're going to switch the camera to the infrared, and these light sources give off gobs of infrared. This one doesn't. And so you'll see a difference in the light here. You'll also see a difference in how I appear in the infrared. So here's how things look in the infrared. And here was a surprise to me. I expected my whole shirt to appear light, because usually the energy of infrared photons is so low they don't interact with organic molecules. But it turns out my shirt had an even bigger surprise, because it turns out the black on this side and the black on this side are different blacks. And this one absorbs the infrared. This one doesn't. In visible light, it looks like it's red on black and then black over here. But in fact, the black over here and the black over here are different blacks, which is truly, truly delightful. So I've actually got three colors on my shirt. I've got black that's also black in the infrared. I've got black that's light colored in the infrared. It doesn't absorb the infrared. And the red just reflects the infrared, and that's typically true of reds. You can also see this light, which is a compact fluorescent bulb, gives off very little infrared. And that's part of the efficiency of these particular light sources. That's a point we'll return to later. But this is how I look in the infrared, which is fantastic. My hair looks white. Oh, my hair looks white all the time. But actually, my hair isn't white. My hair is a color other than white. It just appears white. That's something we'll come back and talk about when we talk about scattering. So I'm sorry that our teaching can't be face-to-face, but I'm glad that I can still incorporate an element that is somewhat personal and that gives me a chance to talk about some of the things near and dear to my heart. I hope you've enjoyed this. Stay tuned for more.